All right, so welcome everybody to our last session for the Christmas workshop. We are very happy to have with us Nima Arkani-Hamed from the Institute of Advanced Studies in Princeton. He's also Severo Ochoa visiting professor with the AFT, so we are very happy that he can be visiting us virtually. And today he's going to, I believe, he's going to tell us how to find positivity by staring at infinity. So please, Nima.
Well, it's really wonderful to be able to join you guys. Thanks very much for the invitation. I've always loved my visits to the IFT, and I really look forward to coming back non-virtually soon. Today I'll be talking about really a body of work that goes back around 10 years. On this sort of general, surprising sort of hidden connection between the very basic, the foundational principles of space-time and quantum mechanics and certain new kinds of mathematical structures that you can really see in the kinematical space that specifies particle scattering processes at infinity, loosely associated with this word positive geometry that I want to tell you something about. And this is a body of work that's been done largely in collaboration with a roughly equal-sized group of physicists and mathematicians over this period. I'm going to do two things today. I want to sort of give you the sort of big picture of what's going on with this entire line of work, and tell you something about the most recent developments, really sort of over the course of the pandemic. Here's a list of many of the people that have been worked on this business for the past decade. If I get to it in the end, the sort of most recent things are based on work in progress with two wonderful young physicists, Giulio Salvatore and Hadley Frost, as well as two terrific mathematicians, Hugh Thomas and Pierre Clemondo. Okay, so to begin with, we've all gotten very used to this famous, beautiful picture that tells us something about the holographic nature of gravity. We've really known since the 1960s on very general grounds that the only observables we can talk about when we have quantum mechanics and gravity, the only quantum mechanical observables live at infinity. And over the last a little more than 20 years, the concrete instantiation of this idea in the gauge gravity duality is in the context of anti-de Sitter space, where we think about the universe in a tin can. Anti-de Sitter space is this tin can, and the kind of observations that we talk about are when we ping the outside of the tin can with we just hit the outside of the tin can and ask what happens. So we look for correlation functions when we ping the outside of the tin can. And of course, the classic picture for how to compute this would involve waves going in to the tin can, banging into each other and coming back out. But we've discovered instead that because the question begins and ends on the boundaries of the box, it's possible for there to be a theory that just lives on the boundaries of the box that gives us the same answer for those correlation functions, and that the interior of the space is kind of emerges as a hologram. So in this picture, you've heard about extensively for over 2 decades now, quantum mechanics is king. The sort of quantum mechanical theory on the boundary is thought of as king, and space and gravity and strings emerge from it. Okay, so that's very beautiful. It's being intensively developed, continues to be intensively developed with lots of new and fascinating ideas and threads of investigation that are being explored. But it's not the real world. It's not particularly close to the real world. And the biggest difference between this and the real world has to do with time. In this picture, time that runs on the outside of the box is the same as the time that runs in the interior. And so this is an eternal universe that sort of lives forever. It gives us an example of emergent space, but not emergent time. And when we come closer to the real world, time matters a lot. So one significant step closer to the real world that we'll talk about mostly in this talk is thinking about flat space rather than anti-de Sitter space. Here, the observables that we talk about are scattering amplitudes. Now we throw particles in from infinity, they bang into each other, they go back out. In asymptotically flat space, these are the observables that we're allowed to talk about when we have quantum mechanics and gravity. They also happen to be the most experimentally interesting observables for particle physics, where we smash particles in essentially from infinity. They bang into each other, they go back out to infinity. But here you see there's no obvious notion of time that lives on the boundary of Minkowski space. We have no obvious notion of locality or time or evolution there. And so it's not obvious what to do if you're looking, if you have this holographic mindset, it's not obvious what the hologram should be for flat space. And things are even more interesting in cosmology, where the observable that we talk about are just, you lie on your back, you look at the sky and you look at the spatial correlations in the distant future. These cosmological correlation functions only depend on space. They involve averages that you see in space today, and we use it to infer the existence of some cosmological history, but really the measurement is done in space. And so if you want a hologram, the thing that should emerge is time itself. But we have no idea what the rules are, even for determining what consistent cosmological correlators are that even approximately have an interpretation in terms of consistent time evolution. So both of these examples sort of highlight that it's unlikely we're going to have some model with sort of quantum mechanics as king and then space emerging. That can't be the only story. And it seems more likely, and this is speculative, but we're going to see more and more evidence, and we've been seeing over the past decade more and more evidence for this speculation, that beyond what we've understood, the kind of next frontier beyond the sort of universe in an anti-de Sitter box gauge gravity duality should involve some new kind of structure out of which both quantum mechanics and space-time emerge somehow together, joined at the hip inexorably. They can't be separated, quantum mechanics and space-time, with the novelty here being time. So that's the sort of big picture goal, and it immediately becomes very concrete when you think about scattering processes. So again, what we want to do from this point of view is the following. Imagine you're talking about scattering processes, and so the world is quantum mechanical, so we can't predict what happens, but we can predict the amplitudes for any process in principle. So imagine you throw some particles in, some particles go out, you're an experimentalist, you do this experiment. The experiment starts and ends at infinity, and you want to know what happened inside which gave rise to the pattern of histograms that you make, all the probabilities that come from the amplitudes. And the theoretical physicist gives you an answer that what happens inside is that the particles go in, they bang into each other, they meet at points in space-time, they bang into each other. So that's locality in space-time. And you have to add up all the possible ways that this could have happened because of Feynman's sort of sum over histories picture of thinking about quantum mechanics. So that's because of quantum mechanics, or the interpretation of these amplitudes, is unitary evolution. So the answer for the question mark of what goes in there that we conventionally have given for the past 60 years is local and unitary evolution in space-time. Okay, and in fact, we've learned over this period of time to even see fingerprints of local and unitary evolution in the structure of the actual functions that are the amplitudes. For example, the amplitudes have certain kinds of singularities associated with virtual particles going on shell. And the structure, the location of those singularities and the properties on those singularities are meant to reflect the local and unitary evolution in space-time and in Hilbert space in a precise way. So what we're going to be doing here is kind of reversing this. So we don't want to answer this question mark by filling it in with local unitary evolution in space-time. We want to find a different question. This question will not live in space-time. It will not live in Hilbert space. It will live in the only space that it should live in, which is the space of the data that labels the scattering process. And in that space, this is the kinematic space at infinity that's referred to in the title, the space associated with the energies and momenta of the particles that make it out to infinity in Minkowski space. In that space, we're going to find a different sort of mathematical question to ask. And remarkably, the answer to this question will end up having all those properties that we normally associate with the rules of locality and unitarity, the rules of space-time and quantum mechanics. But now we'll see those rules as outputs, not as inputs, as derivative outputs from some other more primitive structures. And these more primitive structures are ultimately associated with combinatorial ideas, quite remarkably. And the combinatorial ideas get translated to geometric ideas that then get translated to analytic ideas and ultimately make contact with the rich functions that we actually see as the scattering input. Now, what I've just given you is a very highfalutin sort of philosophical motivation that we suspect, because of quantum mechanics and gravity, that we should somehow lose the notion of space-time in our description of physics, and the strategy is to try to reformulate ordinary physics. We're not speculating about anything, we're just talking about ordinary physics. We want to reformulate ordinary physics in such a way that the rules of space-time and quantum mechanics are not taken as primary, but they come out as outputs and not inputs. Okay, so that's a very sort of abstract set of motivations. But there's a much more concrete set of motivations about that come from what happens when we actually try to compute these amplitudes that people needed to do in order to make experimental predictions for a standard model background at accelerators like the LHC. For example, if you're interested in zillions of new particle searches, you need to understand the backgrounds from the collision of the quarks and gluons inside the protons that we collide at the LHC. You have to understand those rates to high accuracy, and not just 2 particles in and 2 particles out, but very high multiplicities of particles out you actually need. So for instance, if I look at the scattering of protons, or really the gluons inside the protons, here's a process where 2 gluons go in and 4 gluons go out. This happens millions of times a second at the LHC, so you really need to be able to calculate it. And in principle, we know how to calculate it because we have a theory of the strong interactions. And this is the pictures you would draw, the Feynman diagrams that you would draw in the lowest order of approximation at tree level. But you get quickly explosion of algebra. The answer in this case is like 100 pages of extremely hard to interpret algebra. And maybe that's not surprising because it looks like a complicated question. There's no reason a complicated question should have a simple answer, but physics has a wonderful way of rewarding morally good behavior. And the people who did this calculation a little over 30 years ago found that in some special cases, for example, when all the helicities of the gluons are +1, the gluons have spin, they have helicity. When all the helicities are +1, the amplitude is 0. When all but one of them is +1, the amplitude is 0. When 2 of them are negative and the rest positive, these hundreds of pages of algebra collapse to a single term. And I'm not going to explain what these symbols mean here right now. They're roughly the square roots of the momenta of the particles. But this is meant to convince you that the standard way of doing physics, that goes back to Feynman and friends, the standard formalism of quantum field theory, its purpose in life is to make the usual rules of space-time and quantum mechanics as manifest as possible. But in doing so, it's obviously hiding some extraordinary new structure that would tell us where this sort of one-term expression in terms of, instead of hundreds of pages of algebra, come from. And back when this was first discovered, it was not obvious that it was the tip of a huge iceberg. Today, we know it's the tip of an enormous iceberg. And I want to tell you a little bit about what lies underneath this. I want to tell you a little bit more about what we've been discovering about this iceberg over the past 10 years. So, but just to come back again to this picture, we want to find a sort of different question that lives in kinematic space, whose answer are the amplitudes, without talking about summing over Feynman diagrams. And again, I want to stress here, this is not merely some tricks for summing the diagrams better or more efficiently computing the amplitudes and so on. I personally don't care. Personally, other people care, and it's very important for other purposes, but it's not what drives me in this business. I don't care about actually getting the answers to these amplitudes. The fact that the functions that come out are drastically simpler than you'd expect is just a clue that there's a totally different way of thinking about things. But this is not about finding some clever change of variable or some cool trick for integrating the amplitudes or summing the amplitudes. It's about finding a completely different conceptual question whose answer gives you the amplitudes, so that hopefully if we understand how this works, we will begin to learn how to talk about ordinary physics without forcing the language of space-time and quantum mechanics on us. So that puts us in a better position to figure out how to generalize beyond that, ultimately where we suspect space-time and quantum mechanics should really be approximate notions. Here, they're still going to be exact. We're just going to be reformulating standard physics. We're not changing anything, but we want to think about it from a totally different point of view. And so really what we're trying to do is not sort of find the answer, but find a question. We want to find a question in kinematic space whose answer ends up giving us the amplitude. And again, over the past decade, we've been seeing that the nature of this question involves these words, positive geometries in kinematic space. Okay, so roughly speaking, the sort of canvas, again, I'm just saying the same, I'm setting up the question in a variety of equivalent ways. We have a canvas for actually what gives us the data that labels a scattering process. And we can think about that canvas in many ways. For example, I could just specify the physical momenta of all the particles. Let's say I have a bunch of massless momenta. I have n null momenta if I'm scattering n particles. That's my kinematic space, the space of n null momenta. Or you can talk about twistor variables, or the celestial sphere, or coordinates on the spatial future if you're talking about cosmology. But that's the space. You see, in anti-de Sitter space, the boundary is an ordinary space-time. It's an ordinary Minkowski space. It has a notion of time, notion of locality as a metric. These canvases are not like that. They're more unfamiliar. What the heck are you supposed to do in the space of n null momenta? That's the space you're living in. Somehow in the space of n null momenta, you have to find a question whose answer gives us all this richness and complexity of amplitudes that we can interpret as having to do as arising from local evolution in space-time and unitary evolution in Hilbert space. So this is our canvas, and we want to find what ideas breathe physics life into the seemingly very boring and arid canvas. And that's what we've been seeing over the past 10 years. There's this emerging picture that in this kinematic space, there are combinatorial ideas, geometric ideas, analytic ideas, this notion of canonical forms associated with positive geometries that I'll tell you something about. And we've been seeing this in a number of examples. The first example was in the context of n equals 4 super Yang-Mills scattering amplitudes in the planar limit. So it's a special limit of a toy theory. I should say, though, it's a toy theory, but in leading order of approximation, the scattering that we're talking about in this theory, the scattering of gluons, is literally the same as the scattering of gluons at the LHC. So it's a toy theory, but as toy theories go, it's closer to the real world than I think any other toy theory that theorists have been talking about for the past 40 years. So there's a level in the leading order of approximation. It's actually the real world. But you might think it has something to do with supersymmetry or the planar limit or magical features of these maximally supersymmetric theories. Well, a few years ago, we started seeing very similar structures in faraway places from that. And that's associated with these words associahedra that I'll tell you more about in the context of scattering amplitudes. These are now for completely non-supersymmetric theories. And in cosmology, in work with Paolo Benincasa and others, we found these sort of cousins of these geometric structures in cosmology. And it's really the sort of very beginning of this story of the connection between amplitudes and cosmology. But in any case, these objects even appear to exist in cosmology. And I want to stress that these describe real world physics in a reasonable approximation. The world you see when you look out the window, okay? So that world, the real world. And it exposes hidden symmetries and new mathematical structures in this sort of very basic physics. That's one of the things I love about this subject, is that it's pure magic in physics right under our noses, okay? Not like far away and toy places, but really physics right under our noses. All right, so now let me give you some ideas, because we're going to spend most of the rest of the talk drawing pictures and talking about geometries. So let me just first give you an idea what this notion of positive geometry is and how you actually concretely attach it to a function that you can think of as an amplitude. So here's a notion of a positive geometry. It's a very simple idea. A positive geometry is any sort of compact region P in some space that has boundaries of all possible codimension. So the simplest version, in fact, the version that we're spending most of our time talking about, are things like triangles. If you have a triangle, then if the triangle is two-dimensional, but it has one-dimensional boundaries, which are the edges, and it has zero-dimensional boundaries, which are the vertices. So a triangle is a positive geometry. a quadrilateral is a positive geometry. Going to higher dimensions, a tetrahedron is a positive geometry. Any sort of polyhedron in 3 dimensions is a positive geometry. What is not a positive geometry? A circle is not a positive geometry because it has a 1-dimensional boundary, but not a 0-dimensional boundary. Okay, so that's what's special, is that positive geometries are just compact regions with boundaries of all possible codimension. In fact, the boundary of a positive geometry is another positive geometry. Okay, so now here I've drawn it curvy because in the most general situation, and ironically, the situation that we ran into these ideas first, were a much fancier setting where these shapes live in more abstract spaces, they live in Grassmannians, and the boundaries are curvy. Okay, so that's why most generally these things can be curvy. But again, what we'll be seeing today are really the analog of polyhedra. They're called polytopes in general dimensions. So you can really think about them as triangles, squares, tetrahedra, octahedra, higher dimensional polytopes. All right, so those are the shapes. So there's some real geometric shape, but what goes along with it is a particular analytic object. There's a certain differential form that we call a canonical form. And what fixes this canonical form is that it's the unique form that has singularities on and only on the boundaries of the positive geometry P. Now, a singularity, if you have a form in one variable, a singularity, if the form is rational, so it only involves poles and nothing more complicated, no square roots, branch cuts, logs, more complicated functions, just rational functions. But the point is that it's a pole if there's no sort of change of variable that you can do that eliminates it. So for example, dx over x squared, that's just d of 1 over x with a minus sign. So that doesn't really have a singularity. We can just change coordinates and get rid of the singularity at x equals 0. On the other hand, dx over x, we can't do that too. Dx over x is not the d of something rational. So those forms that have so-called logarithmic singularities are special. Those are really irremovable singularities. And so when we have more variables, we say that the form is logarithmic if locally there's a set of coordinates where it can be written as the sort of wedge product of many dx over x's. Okay, so you see there's a real geometry, but we're claiming that associated with this real geometry is a unique form that has the property that the form has singularities on and only on the boundaries of a P. And let me illustrate why that's interesting with a few examples. So here's the simplest example of a positive geometry. It's just an interval. And if I want to ask, and here's an interval in the x direction, so here's I want the inside of the interval between a and b. Well, what is the form that has logarithmic singularities here? Well, obviously it should look like dx over x minus a and dx over x minus b. And note I've put a relative minus sign between them. Why is there a minus sign between them? Because if there was a plus sign between them, this form would also have a singularity at infinity. But I don't want it to have a singularity anywhere other than the boundaries of this interval. So that's why there's relative minus sign between these two terms. Similarly, if I go to a triangle, then the form would just be, again, the obvious thing, dx dy over xy, 1 minus x minus y in this example. So all the poles correspond to the boundaries of the triangle. Now, this is already slightly interesting because let's say I take the residue in x. So I have this form, but I imagine taking the residue in x. So taking sort of x to 0, you can imagine doing a little contour integral around x equals 0. Or more practically, just everywhere you see dx over x, you just get rid of the dx and you set x to 0. So let's say I do that. What I'm left with is dy over y times 1 minus y. And you see very nicely that dy over y times 1 minus y is actually the canonical form for this interval. So here, it turns out that when you take the residue on x equals 0, what you're left with is the canonical form for that boundary, which is this interval now. Now this gets more interesting already when you have something that looks like a quadrilateral. Let's say I have this quadrilateral here. I'm not writing out explicitly the linear equations for these edges. So they're just L1, L2, L3, L4, just some linear expressions in x and y. But now you see what the challenge is, because if I just write this formula down, let's say I put L1 equals 0. If I put L1 equals 0, if I take the residue on L1 equals 0, then the resulting expression could have poles when L2, L3, or L4 goes to 0. Now, when L2 goes to 0 and 1 is 0, that's fine. That would correspond to this point 2. And also when L4 goes to 0, that's also fine. That would correspond to this point 4. But when L3 goes to 0, that would correspond to this funny purple point up there. That's not in my space. And similarly, there's another bad point out here where I don't want to have a residue. Thus, it's not enough to just put these 4 poles downstairs. If I want to have the properties of the form has singularities on and only on the boundaries of the space, I have to have a numerator that puts a 0 on these bad points. So you see already it's slightly non-trivial to get a form that has singularities on and only on the boundaries of the space. And it's even more interesting when you go to a pentagon, there's actually a whole sort of circle or conics worth of singularities that you have to kill. And so you have to have a quadratic numerator that gets rid of all these bad singularities. In general, you see that the singularities of the form reflect the boundaries and the faces of the geometry. And this is very important because we're going to associate the amplitudes with these forms. And so the amplitudes, we're going to get a geometry. You give me the kinematic information of the scattering process. That's going to fix some geometry. And the form is going to actually give us the amplitude. Okay? But we know that singularities of the amplitude are supposed to reflect factorization, locality, unitarity, as we'll review. And the general picture is that all of those properties are actually reflected in something special that happens on the boundaries or the facets of these positive geometries. Now, let's say you wanted to compute the positive, this canonical form for some positive geometry. Then there are a number of ways of doing it, but one way of doing it that we'll focus on in this talk is triangulation. So if you have a complicated positive geometry, if you can break it up into simpler pieces, then it turns out that if the positive geometry is tiled by simpler positive geometries pi, then the canonical form for that geometry is the sum of the canonical forms for the simpler pieces. And so you see what happens in this example is the canonical form for P1 would actually have a singularity on this internal edge. Well, that's not really an edge of the whole P, so it shouldn't be there, but P2 shares that edge. And crucially, because the residue on this edge only knows about this edge, it doesn't know if it came from P1 or from P2. Therefore, when you add these two forms with the correct sign, the singularity in this intermediate part cancels out, and you're only left with something that has singularities on the boundaries as it should. A special case of a triangulation, here the triangles all live inside. There's a special case of a triangulation that you can apply to a broad class of polytopes that's sort of external, actually, and we'll see why this is interesting later. But for example, if I wanted to get the form for a square, I could go to every vertex of the square and draw a triangle associated with that vertex, just by extending all the edges that meet at that vertex and adding an arbitrary line at infinity. So you see, in this picture, I get a triangulation of the square by this big triangle minus this little triangle minus that little triangle, and I over subtracted this one, so plus that little triangle again. Okay. So this gives, and this generalizes to a wide class of polytopes that are known as simple, so that in the neighborhood of every vertex locally, it looks like a simplex, just like it does in this example. And again, every term has a spurious pole at infinity, and they all cancel in the sum. So just keep that in mind. It'll be relevant in a moment. All right, so now we're going to start talking about a very specific class of theories. As I said, the first example of these amplituhedra were in the context of n equals 4 super-Yang mills that are supersymmetric and planar and so on. But now we're going to talk about a totally non-supersymmetric theory. And this is just a theory of some colored scalar phi. So you can think of it as trace phi cube theory. And so the Lagrangian is just trace d phi squared plus g trace phi cubed. Phi is an n by n matrix. And if you're, and so this basic interaction, I can represent the indices for I and j with an arrow for the upstairs indices and an arrow in the opposite direction for the downstairs indices. For the particle physicists, this is a very standard double line notation that goes back to a Took in the 1970s. And that's it. So if you like, this is a toy model for gluons. And you can even get amplitudes for Higgs scattering by taking various linear combinations of these amplitudes that we're talking about. but the sort of color structure and the diagrammatic structure is exactly the same as that of Yang-Mills theory, but the vertices are very simple. We don't have any polarization vectors or momenta. Okay, we just have very, very simple vertices. Anyway, completely non-supersymmetric theory. And there are different pieces of the amplitude that depends on how these color indices are hooked up to each other. For example, at tree level, you just get pictures that look like this. So they're called single trace because all the indices just go around in one closed loop. So you go from here to there, and then from there to there, and as you go around, you just get one closed loop. Here's another single trace term, but now a two-loop contribution to this single trace term. But I can have other, and when capital N is large, these terms dominate at large N. But there are things that are subleading in 1 over n that are associated with pictures that you can't draw on a plane. So all of these pictures are planar. You can draw them on a plane. Here's an example of a double trace at one loop. So it's double trace because you see there are two sets of indices, the one on the outside and the one on the inside that sort of separately connect to each other. So that's double trace. Here is a single trace, but it's subleading. I can't draw it on a plane. In fact, I can draw this picture on a torus, but not on a plane, so it's not planar. It's still single trace, but it would be subleading to these guys by at large N. All right, so now we're going to begin by thinking about this theory at tree level, this trace phi cube theory at tree level. And so just think of it, just at tree level, we don't even have to draw these double lines if we don't want. We're just drawing sort of perfectly ordinary Feynman diagrams, just tree diagrams. But the importance of the color is that the particles are ordered on the outside. So they're ordered 1, 2, 3, and so on, okay? And let's just talk about some nice variables for talking about these tree processes. So if I draw a picture like this, it's actually very natural. We'll come back to this later to see how this is really given to us by the Feynman diagram anyway. But it's natural to sort of draw a dual of this picture. And it's very easy to motivate drawing this picture in the following way. Remember that all the momenta add up to 0 by momentum conservation. So that means that I can assemble the momenta end to end so that I get a picture of a closed polygon. That momentum conservation tells me if I draw this picture, I get a picture of a closed polygon. And now if you think about all the momenta you see in a picture like this, they would just be a sum of consecutive p's in this polygon. So if I label this 1, 2, 3, this internal edge would be p1 plus p2. Okay, so the only momenta that I see are sums of consecutive p's. And the sums of consecutive p's have a very simple interpretation as the distance squared between 2 points in this polygon. So those are my kinematic variables. There are the sums of consecutive p's. So I'm going to call those xij. Notice that xij by momentum conservation is the same as xji. I'm going to imagine the external particles are massless. In fact, I could give them any mass that I like, but just for notational ease, I'll just say that they're all massless. So xii plus 1 is 0. It's simple to show that these xij are not just convenient because they're the propagators we see in the diagrams. They also give you a basis for all of the so-called Mandelstam invariants, all the Lorentz invariants that you can build out of n particles. Okay, and so what is this Feynman diagram in this picture? If I look at the propagators that show up in this diagram, well, they just correspond to chords in this polygon. And you see a legal Feynman diagram corresponds to a collection of chords that gives me a triangulation of the polygon. So if I was a standard quantum field theorist, I would sort of reinterpret the amplitude as a sum over all the triangulations of this polygon. And for every triangulation, I take the product of all the chords in the triangulation of 1 over xij. Okay, so that's the amplitude, at least at tree level, and the lowest order of approximation. Okay, and now let's see how the basic rules of locality and unitarity, where they are in this picture. For example, I'm allowed to see this collection of propagators, but I'm not allowed to see this collection of propagators on the right because these have crossing chords. And the crossing chords correspond to just pictures that I can't draw as diagrams. So, for example, at 4 points, I can't have poles simultaneously in the S channel and the T channel. Locality is reflected in the fact that the only allowed configurations of poles that can come together are the ones that correspond to triangulations of the surface. Unitarity is what happens on those poles. So on these poles, we know that if I send some intermediate particle to zero, then the amplitude should then I've made some virtual internal particle go on shell. The amplitude blows up. It's a resonance. It blows up as 1 over p squared, and the coefficient of that blow up is the product of 2 lower amplitudes. So that's the product of the amplitudes that we dissociate just by cutting this picture and getting this polygon on the left times this polygon on the right. So again, locality is a pattern of allowed chords. Unitarity is what happens when one of them goes to zero to see that this polygon splits into the product of 2 lower polygons. All right. So this is a theory that we're talking about. I've just described how to think about it in conventional field theoretic language. But now let's pretend that we weren't theorists and we're just an experimentalist. And we as experimentalists, and we had access. We could dial the momentum of the particles around any way we like. We could dial them around any way we like, and we want to see what's going on. So we want to do experiments to see what this system is, and what is it that we would notice. Okay, so again, we're not putting in any prejudice that we know ahead of time that it's Spineman diagrams and this trace phi cube theory and so on. What would an experimentalist notice? Well, I'm going to pretend there are 2 kinds of experimentalists in the next few minutes here. Anyone who knows experimental particle physicists especially knows they come in 2 varieties. There are the experimental particle physicists that are secretly want to be theorists, and then there are the experimentalists who just could give a crap about theory. They even hate theorists, some of them. The hero of my story is going to be the second kind of experimentalist, but let's first talk about the first one. So what would both experimentalists notice? They would clearly notice that this amplitude blows up. Okay, they blow up as they move the dials around. They blow up when the Mandel-Salmon invariance, some of them hit 0. Now, the first kind of theorist, experimentalist who wants to be a theorist knows about poles and Cauchy's theorem and residues. So let's say, aha, what I should do is very carefully measure what happens in the neighborhood of the pole where it's blowing up. And if they do that, they would notice, amazingly, that the coefficient of the blow up is given by the product of lower amplitudes that they've measured already. So that's what they'd get excited about. They'd announce that at their conference. And there'd be 2 theorists sitting in the audience. One of them named Feynman, who would say, oh, I know what's going on. What's going on is that what gives rise to this process is the sum of all the Feynman diagrams that I've just named after me. And I'm going to interpret this as particle propagation in spacetime. There's another theorist in the audience, a very famous mathematician named Pierre Deligne, who would look at this and say, oh, I've seen this too. I've seen this too. This happens all the time. It actually, in the very, very first interesting space you study in geometry of just endpoints on a projective line, you discover that the moduli space of endpoints on a projective line on its boundaries, when the points collide, actually factorizes into the product of lower moduli spaces in exactly the same way. That must be what's going on. And it's remarkable that both of these pictures, that for which the sort of factorization is the star of the show, actually do correspond to pictures we've had for 50 years for where particle scattering comes from. The Feynman picture is the one that we teach as physicists in field theory courses, and it's particles in space-time. And Deligne's observation in this imaginary world that this is just reflecting the well-known factorization of this space of endpoints on a line is actually the picture of the string worldsheet. It's the way string theory tells us to think about particle scattering. So if factorization is the star idea that you notice, then you're led to either the picture of particles in space-time or the string worldsheet. But there's a second experimentalist who's lazier but smarter than the first one. The second experimentalist notices that there are poles, but doesn't want to do any very careful measurements, and says instead, look, that's great that the amplitude blew up once. Can I make it blow up more? Can I make it blow up twice, 3 times? And what is the pattern of what I have to do to make it blow up? And they would notice something interesting. For example, for 4-point scattering, they would notice that they have a pole if the S channel goes to 0, or when if the T channel goes to 0, but not both. If they sit on S equals 0, nothing they could do could make the amplitude blow up more. Similarly, if they sit on T goes to 0, nothing they could do would make the amplitude blow up more. For n equals 5-point scattering, then notice it's more interesting. If they set S12, P1 plus P2 squared goes to 0, they would notice that, okay, the amplitude blows up, but then if they set P1 plus P2 plus P3 squared goes to 0, it could also blow up. However, if they set P2 plus P3 plus P4 squared to 0, nothing happens. So they have to only very special combinations of the poles, of the double poles come together. And since they're experimentalists, they want to present this data in a nice digestible way. And they'll discover for these two examples of 4- and 5-point scattering that you can actually represent these observations in the following kind of cool picture. So here is a picture I'll just I'll do the 5-point first, where it's meant to just show you the pattern of the single poles and the double poles. And so here are the pattern of all the single poles that you see. I haven't labeled 1, 2, 3, 4, 5 on the outside just not to be just not to clutter the picture. But this shows that I see this pole where 1 plus 2 plus 3 squared goes to 0. Here it's a different one where 3 plus 4 plus 5 squared goes to 0. So, and the interesting thing is that you can actually put this pattern of poles, this pattern of diagrams, as the edges of a picture. Now, what are the vertices of the picture? The vertices of the picture on this side, I put 1 plus 2 plus 3 squared goes to 0. On this side, I put 3 plus 4 plus 5 squared goes to 0. And so on the vertex, I put them both to 0, and it corresponds to this sort of complete factorization of the picture. So I have the, So I have the partial factorization of the picture. I apologize. I have the partial factorizations on the edges and the complete factorization down to the diagrams on the vertices. So this is not 100% obvious that you can collect all of the singularities of single poles and double poles and represent them graphically like this. You can think of the inside of this pentagon as just no factorizations at all. The analog of this picture at 4 points is even simpler. I have an interval here. The inside is just no poles at all, but on one side I'd have the S channel, on the other side I'd have the T channel. And if we want to try to do this for n equals 6-point scattering, there would be up to 3 poles that I can have. And so if a picture exists, it would have to be 3-dimensional. In fact, such a picture does exist remarkably. Okay. Now I'm drawing the same thing in the language of triangulations of the corresponding polygons instead. But there is this remarkable picture at 6 points, and in fact at any point. So I've drawn it here. In terms of the diagrams, I'll draw it in terms of triangulations in a second, but it's the remarkable fact, not at all obvious, it was discovered by mathematicians in the 1960s, that it's in fact possible to represent all of the pole structure of the diagrams, or equivalently, all the triangulations of this sixgon, so that as the vertices, edges, and faces of a 3-dimensional shape that's known as the isosahedron. Okay. So here is another picture of it. Again, I haven't drawn everything just not to clutter it too much, but you see that the vertices correspond to triangulations of a hexagon. This edge is a partial triangulation with only 2 chords, and this face is an even coarser triangulation with just 1 chord, and the interior is no triangulations at all. And the claim is that this picture fits together consistently. Okay, so this edge would have that chord, this one would have another one, and they meet on an edge where they both exist, and 3 of them meet at a vertex where all 3 of them exist. Again, this is not at all obvious that this is possible to do, but it is. And what's fascinating is that this picture is not made obvious by either the particle or the string picture of the world. Okay, so the sort of proof is that most of us have never known this fact. It's a very basic fact about the pattern of poles that can come together that reflects the pattern of poles that can come together can be given this geometric shape. Okay, but not only that, this picture, again, it's known as the isosahedron. The isosahedron actually knows about factorization as well, and that's because remember. Let's just see qualitatively how it sees it, and we'll see it a little more quantitatively in a second. That factorization, locality, unitarity, and reflected in factorization, which tells us that when I go on a pole, the amplitude splits into the product of 2 lower amplitudes. Well, that's reflected here by the fact that the boundaries of the isosahedron actually look like the product of 2 lower isosahedron. So let's see how that works in this example. So notice this face here looks like a pentagon. Okay, that This face looks like a pentagon. And remember, the pentagon is what the 5-point isosceledron looks like. Okay, so if you look carefully at the picture, there are 6 pentagons and 3 squares. The 6 pentagons correspond exactly to these factorization channels with 3 particles on one side and 5 on the other. What about the squares? The squares correspond to these factorization channels. There's only 3 of these. That's why we only have 3 squares. And remember, every square is an interval, and the direct product of 2 intervals is a square. Okay, so this shape not only tells us something new that we didn't know before, that the sort of pole structure is captured by this geometric shape, it also tells us what we did know before, which is factorization. It's all captured by the existence of this rather remarkable object. Okay, so that's a sort of an early clue that there's something interesting going on. Particles and strings don't know this. Okay, but it exists, and the object, but the object that makes this manifest does know everything that particles and strings knew. It knows about factorization. So this is just a first clue of some structure we want to see in kinematic space. Again, this lives, it's just a statement about the poles that come together in kinematic space. How can we make this obvious? And trying to make this obvious is going to be, we're going to try to make these things obvious, and it's the qualitative clue to the theory that we're looking for in kinematic space. Now let me give you a more quantitative clue. This is a little more interesting. It's a little sharper. And all these things end up being related to each other. In fact, the existence of this sort of master positive geometry in kinematic space explains all the things that I'm going to tell you in the next few slides. But again, these are just sort of clues that you can, in principle, have noticed. These amplitudes, for even these dumb, boring scalar field theories, there's nothing special, no supersymmetry, no gauge invariance, no the dumb, boring scalar theories. They have a hidden symmetry that we had not noticed before. And so let me, in order to show the symmetry as obviously as possible, we're going to actually upgrade from thinking about the amplitudes to thinking about certain differential forms. Okay, so here's what we're going to do. For n equals 4, instead of writing, here I'd write down 1 over s plus 1 over t. In the language of these, of the chord variables, this would be 1 over x13 plus 1 over x14. But instead of thinking about a function, we're going to think about a form. So I'm going to think about dx13 over x13 and dx24 over x24. So you draw the same old Spineman diagrams you always did, except you do dx over x instead of 1 over x. Now comes the question, because they're forms, what signs should I assign to each diagram? And the answer is that something interesting happens in this case if you assign a relative minus sign between the two of them. And why is a minus sign good? Because in this case, if you put a minus sign, you notice that the form is only a function of the ratios of 1, 3 to 2, 4. In other words, you might expect that the answer only depends on the ratios of these invariants and not on some absolute scale. If you want the form to only depend on the ratio and not the absolute scale, something we would call projective invariance, that says that the form is invariant into these local transformations where you rescale the xij by any function of xij, then that's only possible if you put a relative minus sign. Okay, now in this case, it seemed trivial. There's a choice, I made one, and it makes it work. But in fact, as you go to higher n, you discover there are many, many more equations than unknowns. If you just put random signs and you just try to solve for the signs, there are many, many more things that have to cancel. And so you can't just hope that just by equation counting, it's always guaranteed to be able to do it, not remotely. However, amazingly, it turns out it is possible to do it. It's remarkable the signs can be chosen so that this form is projective. So this ability to choose the sign so the form is projective turns out to imply that the amplitudes sort of vanish in some direction as you go to infinity more quickly than you would naively think from every Spineman diagram. We'll come back to that, this fact in a moment. And it's an analog of a similar symmetry known in n equals 4 super Yang-Mills as dual conformal invariance. Except here it has nothing to do with supersymmetry or integrability or anything like that. This is just some universal fact about propagators. It's not even really about the scalar phi cube theory. It's something about the way all the propagators can fit together in these diagrams tells us that we have this hidden projective invariance. At the moment, at tree level, we'll come back in general in a sec. So these are, so this is a certain form that we associate with the diagrams. And to get the actual amplitude, there's an extra fact that that I take this sort of form. In this case, for n equals 4 scattering, I have this form that lives in the space x13 and x24. It's a 1 form. How can I get a number, a function out of a 1 form? I can pull it back to a subspace. And in general, for general, and so in this case, it's a very simple subspace. You can just guess x13 plus x24 equals constant. And if you pull back this form to the subspace, then the minus sign goes away and you get the function 1 over x13 plus 1 over x24 that we can interpret as the actual amplitude. For general n, it turns out there is also a subspace of this sort. These ideas and the connection of the icosahedron with the phi cube theory was pointed out in a paper with Yuntao Bai, Song He, and Gangwan Wan back in 2017. And these objects are now, by the mathematicians, called ABHY polytopes, ABHY icosahedra. So there's a subspace we can pull back to where this phenomenon happens, where we on that subspace, all the minus signs go away and we get a function which is just given by the amplitude. Okay, so this is also not obvious. So the symmetry is not obvious. The fact that there's a subspace you can pull back to where all the signs go away and you get pluses from this form is not obvious. And but this all happened in this realization that we found, that we stumbled on as physicists of the icosahedron. So you'll notice that so this is the picture that we got back in 2017. It's a very specific form of this general shape. Okay, so you'll notice that sort of combinatorially, the facet structure of this shape is the same as this one, but this is a very specific shape. There's lots of parallel sides. It's a very specific version of it. And that's what we found back in 2017. And it turns out to be associated with all sorts of interesting mathematical objects, cluster algebras, polytopes, associated with Dinkin diagrams, and so on. But for our purposes, again, we want to understand, back in 2017, we made some sort of guesses to get this polytope, but we want to sort of understand more deeply where this comes from. So it's another clue to the theory that we're looking for in kinematic space. We want to find not just this icosahedron in kinematic space, but some question in kinematic space that's naturally going to spit this out, rather than just guessing as we did back in 2017. Okay, so I see that I have something like 10 minutes left. I think so that's the setup. So I think what I'll do in the next in the last 10 minutes is just sort of flash what some of the ideas are. First, at tree level, I'll try to explain it a little bit more, but then I'll just sort of give you a flavor. We'll just sort of very quickly go through some slides, just give you a flavor of what we've been doing first towards the end of last year, and then largely in the pandemic. This is what our obsession has been, is to extend these ideas to all loop order, and some surprises come out as we do that, as you'll see. Some surprising connections with gravity and string theory are going to emerge. But let me first just give you a flavor of how things work even at tree level. So I hope now you have some, our challenge, I hope, is clear, right? Our challenge is, we have this kinematic space. At tree level, this kinematic space is just the chords of a polygon. That's it. In the space of chords on a polygon, somehow we want to ask a natural question that spits out these sort of funky objects, these polytopes, and the canonical forms of these polytopes will give us the scattering amplitude. Okay, but we have to figure out how, starting just from chords on a polygon, we're going to get these cool shapes. And so the first observation just comes from just listing the variables. Okay, so if you want to list all the variables, here I have the chords on the polygon, 1, 3, 1, 4, 1, 5, and so on. I'm just going to write them down. Okay, so obviously I can put them on a grid. The indices are ij, but remember that x1, 2, 2, 3, 3, 4 are 0. Okay, so if I do that, let me start with any one of them, like x1, 2, and now I'm going to move in one index in this 45-degree line, another one in the other 45-degree line. I could have drawn it more normally, so the axes were horizontal and vertical, but it doesn't matter. I've just chosen to draw it this way for convenience. And so remember, I'm putting in black the guys that are 0. So 1, 2, 2, 3, 3, 4, etc. is 0. And then if I just clock the indices up, and you see this is the picture I get: 1, 3, 1, 4, 1, 5. Here, this is n equals 7 scattering. So there's 1, 7 here at the top is 0 again. So you see that I get this strip, which is bounded on two sides by zeros. And inside, I have all the things that are non-zero. And you'll see something sort of interesting, that down here, I get 1, 3, but up there, I get 3, 1. Okay, so remember, 1, 3 and 3, 1 are the same. So this strip, if I imagine sort of drawing it in a continuum, this strip has a Mobius symmetry, where the point xt and 1 minus x, 1 plus t are the same. Now, here already, I've done something a little bit, I've done something a little funny. I've given this direction, vertical direction, the name t as if it was time, and this direction, the name x as if it was space. And in fact, we will see that there is kind of a kinematic space-time here. And the first hint that there's something interesting to think about this direction as time is simply the following. Remember that it's going to be important to us whether two chords cross or not, right? So remember, we're not allowed to see two crossing chords. But we can ask, in this space of the polygon, when two chords cross, what does it mean about the relationship of the points in this strip? And the answer is very simple. The chord ij crosses KL. If I plunk down ij and KL, and if I think of this direction as time, they cross if the future light cone of ij intersects the past light cone of KL. In other words, if ij and KL are the past and future corners of a causal diamond that fits inside this strip. How could this fail? Well, they could be space-like separated. That would correspond to ij and KLs that don't cross, or if KL is so far up here that the past light cone from KL doesn't intersect the future light cone from ij. Okay, but if ij and KL are the past and future corners of a diamond that fits inside the space-time, then the corresponding chords cross. Okay. Another thing that we have to do is choose some particular chunk out of this mesh in order to cover all the variables once and only once. So the easiest thing, I've given you various ways we could do it, but anyway, here's one simple thing we can do, is just a sort of right triangle picture. Okay, so we have this right triangle picture. Notice 1, 3 is inside, but 3, 1 is out here, is outside. Okay, so again, nothing is happening here yet. We're just labeling our variables, nothing else. We're just labeling our kinematic variables, but already something a little interesting is going on even with the label. All right, now that we're done labeling, now we have to find a question to ask in this space. And the question is going to turn out to be a very simple and familiar one. We're going to solve the wave equation. Okay, so we have this sort of kinematic space-time. We have, so already somehow we have a notion of time and space just built into the labeling. So we're going to just solve the wave equation. And if I use the usual u and v variables for the 45-degree directions, it'll just be du dv x equals c. And then there are very simple facts about the wave equation in 1 + 1 dimensions. For example, there's an analog of Gauss's law that tells you that past plus future minus left minus right is equal to the total source contained inside this causal diamond. Okay, and then there's another rule that I don't have time to explain.
Sorry.
But yes.
Does the continuum limit mean anything in these pictures?
Yes, it does. Yes. We can maybe I can come back to this question in discussion. Yeah. So we're really thinking about the continuum limit, and then we're going to sample the values of the solutions of this wave equation at a finite number of places. That'll take us back to the old. That'll take us back to the grid picture we had before. Okay, but you can imagine making the grid picture finer and finer and finer to go to the continuum limit, if you like, and that will correspond to scattering of more and more and more particles. But now we're going to do something else. We're going to solve the wave equation. We're going to inject the word positivity, and this mirrors something we've seen everywhere in this story, in this general positive geometry amphipohedron story. You go to your kinematic space. It seems like a totally boring place. And then you say the word positivity in some appropriate way, and then magic begins to happen. So in this case, we're going to say that we're looking for solutions where the source C is positive and where X remains positive. So for instance, you can see that if I specify the values of X on the sort of past future of this triangle, it specifies what X is everywhere inside. But I want the C to be positive everywhere inside and X to be 0 on these two edges. Remember, on the boundaries, on this boundary and on that one, X is equal to 0. But I want to put some constraint on the boundary values here so that X stays positive everywhere inside. Okay, and here's the remarkable thing that happens. If you do this exercise, this looks a little bit complicated because I have to put constraints on a function of a continuous variable here. So you can instead ask, let me just sample this at a finite number of points, okay, and see what constraints I can put on the values, let's say at sort of 3 different points here on the past boundary. Okay, so if you do that, so let me plonk down these 3 points. And obviously you should shoot out the light rays from these points. Obviously those are going to be important. So you make this sort of interesting grid. And all we're going to do is ask for positivity, not everywhere in here, but for the points here, as well as for all of the points that have shown up in the intersection of all of these light rays. The amazing thing is that if you do that, just asking for all of these points to be positive, which you can get just by applying this Gauss's law formula to compute the rest of the points, you can then plot what region in 1, 3, 1, 4, and 1, 5 space is allowed so that the solution everywhere inside is positive. And amazingly, the answer is exactly the isosahedron. Okay? So the isosahedron is actually the answer to this question of solving the wave equation in the kinematic space. And that's it. And then the amplitude or the canonical form is fully determined simply by asking that when you find a form on the full kinematic space such that when you pull it back to the solution of the wave equation, you get the canonical form for the isosahedron. Okay? That's it. And factorization has a one-line geometric argument. So, you know, this picture makes manifest that we're building some kind of polytope that lives in kinematic space. But it also makes manifest that that polytope has a property that when you go to its boundaries, it factorizes into the product of 2 lower polytopes of that type. It's a one-line argument. The sort of crucial thing is the following. That if you imagine going to a boundary of this space, it's like saying that X somewhere in here, instead of being positive, is 0. But once it's 0 here, then you can show that it cannot be 0 anywhere inside these red regions. And it can't be 0 in those red regions, again, crucially because of this Gauss's law constraint. Gauss's law tells me past plus future minus left minus right is the total charge. But if everything is positive and the charge is positive, I can't put both the past and future corners to 0, because then I'd have the sum of 2 negative things equal something positive. So that tells me that I cannot set the things inside here to 0. And then a one-line argument tells you that you can actually completely characterize the space of all x's that are allowed on the remaining boundaries just by scrunching away these regions and taking the product of 2 smaller pictures of exactly the same type. So that was the sort of goal. Remember, we want to see why is there a polytope that factorizes on its boundaries. That's what knows everything. Asking for this positive solution to the wave equation in kinematic space already automatically gives me something polytopal, and the fact that it factorizes to its boundaries is a sort of trivial consequence of this setup. Okay, so and as I mentioned, the scattering amplitude is the canonical form, and all of those properties that I mentioned, it's trivially projectively invariant. So there is that hidden symmetry. The hidden symmetry is made obvious by the fact that the polytope doesn't have any singularities at infinity. It only has singularities on the facets of the polytope and nowhere else. The fact that on the subspace you get the amplitude is also obvious from more interesting properties of the normal facets of this ABHY isosahedron I don't have time to talk about in detail. But I want to stress there is one particular triangulation of these polytopes, which are the ones that I mentioned early on. It's a kind of a universal triangulation of broad class of polytopes, where you go to every vertex and you look at the simplex that you get by drawing all the faces away from the vertex and chop off at infinity. Okay, so remember I showed you this picture for triangulating a square. you can do this. You can also do this for the icosahedron. And this triangulation has a name. It's called Spineman diagrams. Okay. Remember, every vertex of the icosahedron is associated with the triangulation of the polygon. And so this is one triangulation which manifestly looks like the sum of all Feynman diagrams. However, you also see that's a very nice triangulation. It's a perfectly general and good one. But you see what its defect is. Every term has a spurious pole at infinity that breaks this projective invariance term by term, and only the sum of all of them is projectively invariant. And in fact, there are many other triangulations. There are other triangulations that manifest projective invariance term by term and are actually vastly more efficient than Feynman diagrams. I mean, literally, you can get the amplitude, you know, ridiculously more quickly with these other ways than just by summing up the diagrams, even for this dumb phi cube theory at tree level. And I haven't focused on this efficiency aspect here, but it's an interesting fact. This has teeth. This business is not just moving equations around and interpreting things a different way. It really gives you new formulas and new insight, new symmetries, and those give rise to new formulas. In fact, there are other methods for computing the canonical forms that don't involve triangulation. There's a general method that actually introduces a parameter that you can think of as alpha prime. And fascinatingly, when you apply that general method to this particular icosahedron, the function that you get is the string amplitude. Okay, so it adds an alpha prime, but what you literally get is a Kobe-Nielsen amplitude. There's no picture of a worldsheet. There's no obvious worldsheet here. There's a question you're asking directly in kinematic space, but if you look at this more general way of determining canonical forms, you get string amplitudes. All right, so I think I'm out of time. I've sort of told you that the kind of story as it stood in mid-2019 up to the sort of picture. I mean, the papers came out in December 2019. Maybe I'll just sort of very quickly flash through just in a few minutes, just so you have a flavor of what's been happening since then. If you keep going with this picture of time evolution, if you keep going with this picture of the kinematic space-time, there's another very natural physical thing that you can do, which is to sort of think about not using Gauss's law to determine all the points, the values of all the points inside, but literally using time evolution, sort of from one Cauchy slice to another. And when you just think about labeling Cauchy slices, it's actually very naturally associated with pictures like this, where the nodes, the arrows, the direction of the arrows just denote whether a point is in the past or the future of the other. And you discover that time evolution is more abstractly associated with drawing one of these pictures and then taking every node that's a source and reversing the arrow so it turns into a sink. And every time you do that, writing down the sort of little Gauss's law equation, which it looks like x plus x prime minus the sum of all the x's that would point into your, would point out of your source, set to some constant. Okay, so this is again doing exactly what we're doing before, but now interpreting it as time evolution in this space. And once you do that, you can abstract that rule away. You can abstract this rule for time evolution away to actually not just what you get from this picture, but with any tree-like picture. And the remarkable thing is that it turns out that this rule only sort of stops and doesn't keep on going forever and builds a closed polytope for very special quivers, which turn out for very special pictures of nodes and arrows that turn out to be Dinkin diagrams. And this connects up with the so-called story of cluster algebras associated with polytopes. And I don't have time to explain, but it turns out that the classical Dinkin diagrams for AN, BN, CN, and DN, the polytopes that you get are actually directly interpreted as physical amplitudes, tree amplitudes, amplitudes that emit at one loop tadpoles, and full one loop amplitudes for the case of the DN quivers. Okay, so and this is all connected up, and then beyond one loop, starting at two loops and above, and non-planar, something new happens, but they're clearly somehow connected to this notion of surface cluster algebra of punctured surfaces that I'll say a tiny bit about. But just so you have an idea of what's going on at one loop, we do exactly the same thing as we did before at one loop. We just draw all the kinematic variables. Now I would draw, for example, for 4-point scattering at one loop, I would draw this Feynman diagram with a square. This would be the sort of dual diagram. So I have some of the variables that we had before, like these arcs. Now they're no longer, ij is no longer the same as ji, because it can go around this sort of hole in the middle in two different ways. The loop variable would just correspond to something that goes to the puncture. A tadpole variable would be something that corresponds to something going around like that. And it turns out that that you have to introduce a second kind of loop variable, kind of a copy of the first one that goes to the puncture. This is actually natural because really you should think of this thing, this is a hole in the space. So you can't really just go from here to a hole. You're sort of spiraling around it. And so it depends whether you spiral around this hole in one direction or the other. That's the distinction between these two different things. But anyway, you figure out what the kinematic spacetime is, you draw the variables, and again, you look at the solution of the wave equation. And there are some little extra decorations that are associated with the fact that there are these two kinds of variable. But you draw a very similar picture to before. You again just write all the Gauss's law formulas. You ask for the solution to be positive everywhere inside, and amazingly, tuck, you get this picture. And the remarkable thing about this picture is that every vertex is associated with one of the Feynman diagrams. You get all of them. You get this one, you get the one with bubbles, you get the one with tadpoles. All of them come out. We didn't put in anything that looked like space-time processes, diagrams, nothing. We just had this kinematic space of the arc variables, but just asking this positive wave equation statement in the space tells us that it's space-time processes that are interesting. These are the vertices. And it also tells us there's a master object that puts them all together. And that's the quantum mechanics. That's what tells us we have to add them all up together. And the canonical form for this object is, again, the amplitude. And anyway, and there's even, there are ways to chop this object to remove this doubling of the propagators if you like, although it's just a factor of 2, so it's not important. Beyond this, when we go in complete generality, we have to think about Feynman diagrams that are drawn on general surfaces. And so this is a very sort of basic fact that, again, known since Atoft, that general diagrams are drawn on general Riemann surfaces with boundaries and punctures and certain genus with a very simple dictionary. In fact, it's more fundamental than that. A single diagram actually defines a surface. Even one Feynman diagram defines a surface. If you take this particular vertex, you can think of it as defining a triangle, where the vertices of the triangle are the labels, the color labels of the double line notation, and the edges of the triangle are the edges of the diagram. So, for example, if I draw this diagram, it's defining this particular triangulation of the square. If I draw this diagram, it's defining another triangulation of the square, but a single diagram literally defines a surface just by gluing together each one of these triangles. Okay, so that's the sense in which we know that we're really thinking about the diagrams, the duals of these diagrams are literally the surfaces. And therefore, our kinematic space is just literally the space of arcs on surfaces. Okay, so we already saw it at tree level, it's just arcs that look like that. At loop level, this would be some triple trace, 2-loop thing, and here are some sample arcs. This would be single trace, 1 loop, subleading in 1/n, so I draw it on a torus. Again, the kinematic space is the space of all the arcs on the surface. And in fact, the momenta that you assign to any arc are read off from the homology of the surface. So this just generalizes what we saw before. In the case we had before, I want to know what momentum to assign to this arc. And notice that this arc is actually homologous. I can just contract it to be the same as the sum of these ones on the outside. The ones on the outside I assign momenta to, and therefore the momentum associated with this arc is the sum of the ones out here. It's more interesting on with more complicated topology. For example, here's a case of an annulus. And once again, I would assign momenta to the outside, to the inside, and let's say to this variable, I call this one L. Then the momentum for this variable here would, this new one is homologous to the old one, plus this one, plus that one. So its momentum is L plus P1 prime plus P2 prime plus P3 prime. Notice the interesting thing, this guy is the same as this one, except it winds around once. And its momentum is also shifted by the sum of all the momenta on the inside. This is in fact a famous problem when you draw non-planar Feynman diagrams. If you want to imagine you're talking about an integrand that depends on a loop momentum, it's not obvious how to label the loop momenta in different diagrams together. And the picture of the homology on the surface solves this problem. It tells you how to label them all together, but now something happens that you have to allow for the possibility that the same sort of variable is related with many different winding sectors to each other. I should also say that in this picture of momentum as homology, momentum conservation is just the fact that a trivial closed loop is homologous to 0, okay? All right, so that's our kinematic space. It's a space of arcs on surfaces. We know how to assign momenta to every one of our kinematic variables. And so now what we want is on various spaces, trees, 1 loop, 2 loop, this is torus 2 loop with one of Ren corrections. We want to see, is there a kind of a question in kinematic space that gives rise to these surface amplituhedra? The isosahedron is the sort of simplest case at tree level, and it existed and was understood somewhat was understood in a variety of ways mathematically. Even these 1 loop objects were associated with cluster polytopes, and we gave a new realization of them and a different way of thinking about them, but they're objects that were known to exist mathematically. Beyond 2 loops and above is wild territory. So that's what we're looking for, is some analog of all these things in total generality. And I don't have time to talk about the specific, there's a number of general and sort of beautiful points here, but let me just tell you what the nature of the challenge is and how we've been finding and what the resolution looks like. The nature of the challenge is that the second you start getting 2 punctures, or even the case of an annulus, the second you go beyond planar 1 loop, you have to deal with the fact that there are infinitely many variables. And for example, this is what would correspond to 2 loop processes, and it's what we saw before. Here's an arc, but here's another one that winds around this puncture once, or winds around any number of times. So we have infinitely many copies of what looks like the same propagator, but they're different topologically. This reflects the action of the so-called mapping class group on these surfaces. And so it's that infinity that you have to deal with. Now we claim that there is such a thing as the surface amplituhedron that deals with this infinity in an interesting way. And in fact, you discover it by following your nose and doing essentially what we did before. So this is the first case where something interesting happens, is the case of the annulus diagram. You can think of it as double trace 1 loop. It's a particular class of so-called cuts of the integrand in all loop order. It has variables, just like we talked about, the variables that go from the, that connect the guys on the outside to each other, out, or in, as well as these variables, the in, out, that connect the inside to the outside. And it's these guys that can wind around arbitrarily many times. And an absolutely critical thing to the story ends up being talking about another variable, this delta, which is a closed loop that surrounds the annulus. Now, notice a crucial thing about this delta. It is not ever a chord of a Feynman diagram that you would draw. All the chords of diagrams that we would draw are things that connect different boundary components. This delta is something new. Okay? But notice that the momentum that I was assigned to this delta by our rules, this delta is homologous either to the outside or the inside. So it just be the sum of all the momenta of the outside or the inside. So just keep that in mind. This delta is not an ordinary variable, but it turns out to be a crucial part of the story. But you discover it all by going back to your space-time pictures. If I look at these in-out variables and I once again just draw them all, now because they can keep winding forever, I actually see an infinite cylinder of these variables. If I look at the variables that connect just the outside to the outside or the inside to the inside, then I get a finite cylinder of these variables. And in all cases, I just write down the wave equation, Gauss's law, exactly the same things I did before. But now I have this infinity that keeps on going forever. So an obvious thing to do is to just stop somewhere. But if you stop somewhere, you find that you don't have a closed polytope. There's something missing. And it turns out that something that is missing is exactly this variable delta. Okay, so this thing that was sitting there on the surface is actually needed in order to complete the picture. And I don't have time to explain how it works in detail, but there is really a picture that looks like this, that this delta is forced on us by the positive geometry. this surfacehedron that we're filling, this is what would happen in the case of an annulus with 2 points on the outside and 1 point on the inside. So it's a double trace amplitude at one loop. And you see, you get all these beautiful faces, and I add more and more windings. I can get more and more and more of them, but no matter how much I add, there's a hole. And the hole is exactly filled in by a piece of the geometry associated with this closed loop instead. So this delta object is forced on us by the positive geometry. And remarkably, delta is interpreted as something like gravity. I'm putting quotation marks around gravity because for one thing, we don't have any polarization vectors. Everything is scalars here so far, but it looks a lot like gravity, and also a lot like the way gravity is discovered in string theory. So gravity is discovered in the scattering of open strings in string theory in exactly the same annulus diagram, by the fact that even though you didn't want it, there's a pole that is associated with closed string propagation when you compute the one loop open string amplitude. And exactly the same thing is happening here, except there are no obvious strings. I'm trying to build this polytope, and I discover that it has a hole. I have to put in this delta to fill the hole, and that delta gives me a new pole. Now, the interpretation of that pole is beautifully simple from the geometry. It's just taking the surface and pinching the closed loop that goes around the inner annulus. If you imagine pinching that, what do you get? You get a new puncture at the pinching point, and then you get a product of a disk with a puncture on one side and another disk with a puncture on the other. That's exactly what we'd expect. That with a new pole corresponding to a new particle, again, this was not one of our old poles. It's a new pole, it's a colorless particle, and it links the annulus on the outside to the annulus on the inside in exactly the way that you see in string theory textbooks. Now you can keep on going. Here is another object, a two-loop triple trace part of the amplitude. Now you see there are three of these deltas that we can imagine drawing that are closed loops around each one of these three boundaries. Now you go through the same process. Every one of those deltas has to be filled in, but now the geometry forces on you a particular facet where the three deltas meet. And that's not obvious a priori, but there's a facet where the three deltas meet. And in fact, the facet structure of these surfacehedra is perfectly capturing the cutting of the surface, and where the interpretation for the deltas is the pinching of the corresponding curves. So in this case, the pinching of the corresponding curves is really like a disc here, a disc here, a disc here, and they're glued with a three punctured sphere, or drawn a little bit more impressionistically, there's three poles for each one of these deltas, and the result is non-zero. So this would be interpreted as all of these colored guys on the outside producing three uncolored guys with all their poles and some non-trivial interaction. Okay. So these deltas look gravitational. In fact, there's even a notion of a coupling constant that you can associate with them. If we keep a lot of the winding sectors, but not infinitely many of them, if we stop somewhere, then the amplitude would be given by this total number W times the sum of the phi diagrams plus these phi delta interactions and the delta delta interactions. But the phi couples to the deltas with some kind of coupling that's down by this power of how many windings I kept. So there's even a parameter that you can dial that makes this sort of gravitational sector as weakly coupled as you like to everything else, but still you can't avoid it. It's there, it's forced on you by the geometry. So that's what we've been working on over the course of the pandemic, and I think we've arrived at a conjecture that we've been actively testing for the past month or so. So far, everything is working, but we're still in the middle of testing everything. So we're currently testing a conjecture for surfacehedra that will be attached to any Riemann surface. And so that's the same as giving a non-supersymmetric, non-planar, all-loop amplituhedron for this trace phi cube theory. And there are these two surprising features. One of them is the sort of forcing of gravity associated with these deltas, something like gravity, and we want to interpret precisely what the analogy should be, but it's very much like something very much like gravity. And secondly, obviously, there's a lot in this business that's very stringy, seems very, very stringy, but there are no obvious strings anywhere. And in fact, the usual picture of the string worldsheet does not know the things that I'm telling you about the amplitude. It didn't know about projectivity. It didn't know about the fact that all different ways to answer. Didn't know about the polytopic structure. Somehow it seems like there's this more sort of primitive object that's associated with Riemann surfaces. And it would be fascinating to understand how precisely it's connected to string theory. If it maybe even gives us a different way of thinking about what the worldsheet string theory is. That's very speculative, but certainly there's an aspect of this story which is very stringy, but there's not an alpha prime in sight in anything that I'm telling you about. And I think that's extremely interesting and worth trying to understand better. All right, so there's a novelty, which is that when we go beyond the examples that I've been telling you about, the evolution in kinematic space becomes cosmological. What I mean is that all the pictures so far, there's something that kind of look like a flat space-time, like these kind of pictures, these Gauss's law and flat space-times. And already when you go to the case of things on the torus, you find that these space-times sort of grow exponentially. It looks more like inflation. Or if you go to 3 loops, even in the planar case, it even looks like false vacuum eternal inflation. You get these branching processes that go on independently in many places. And so that's extremely interesting, and it adds a number of novelties to the subject that we're trying to understand. But anyway, as I said, we do have a conjecture for the whole story, but we're still checking if it works in all examples. All right, so let me end. I'm so sorry I've gone on so long, but just a few quick points. Over the past few years, we've been seeing, I think, very concrete examples. These are not just slogans. They're very concrete examples where the rules of space-time and quantum mechanics, locality and unitarity, are seen to emerge from simple new structures in kinematic space at infinity. And at all loops in the planar limit for n equals 4 super Yang-Mills, this is the story of the amplituhedron. In fact, what really triggered many of these developments was around 3.5 years ago. We understood that we could think of the amplituhedron itself in kinematic space. Previous to that, it was living in some auxiliary space, and it was only around 3-4 years ago that we realized it actually lives in kinematic space. Once we realized it lives in kinematic space, it made it possible to look for these structures in kinematic space elsewhere. Then we have these completely non-supersymmetric trace phi cube theories. And I think we're heading towards an all loop, all orders in 1 over n picture for these surface amplituhedra. And what I find sort of important and exciting about these ideas is that, as I said at the start, they're directly related to real world physics in reasonable approximations. They expose hidden symmetries and describe universal features of wide classes of theory. But it's still also very much an experimental subject. You know, we have a few examples of how these positive geometries arise. And another thing that's happened in the past couple of years, actually really in the last year, is that year and a half, is that there's starting to be hidden connections between amplituhedra for n equals 4 super Yang-Mills on the one hand, and these surface hedra type objects on the other. So they seem like sort of two different things, even, but there are subterranean connections between them that are both mathematically and physically fascinating that are starting to be discovered. So I think we're not yet in possession of, maybe not even close to possession of, what the sort of, if they even exist, what the simple universal sort of principles are that all this magic comes from. But it's 100% clear there's an ocean of magic here. It's related to the real world. And I think it'll be very interesting to sort of keep going and see where the summit is and what the view will look like when we get there. Thank you very much.
Okay, thank you, Nima, for this tour of strange places. So, are there questions?
I will ask a question if I may. This is Alvaro.
Go ahead.
Good evening. Those things that you call X and T, do they have something like a Lorentz symmetry?
Well, to the extent that, yeah, they would in the continuum limit. I mean, it's to the extent that the only equations that we're talking about are the Gauss's law equations, then yeah, but they're all discrete. So when you sample at a finitely many points, we're just getting the they're free and they're discrete. So they don't have a more useful Lorentz symmetry than what you just get from Gauss's law for one plus one dimensions.
Okay.
Oh, I see Jim Stashev is here. I should have mentioned that this polytope was discovered by him in the 1960s. So great seeing you, Jim. The isosahedron was discovered by a Jim. Normally I say a Jim, I just forgot in this talk. No, I know. You're the least credit hound person I know. So, but it's wonderful seeing you.
No, I wasn't looking for my.
No, I know. I just, but since I saw you, yeah, it jogged my memory. Yeah, very nice seeing you.
My pleasure.
Other questions?
How does one access the recording?
It will be put on our YouTube channel, the IFT YouTube channel. So if you visit the webpage of the conference, you will get directions to
The conference, right?
Just
Very
type
good.
YouTube IFT and you will find there everything.
Excellent.
I can't remember if I'm remembering this correctly, so maybe you can correct me if I'm wrong, but I thought you told me at one point that your original paper on the isosahedron was rejected by the referee because they thought it was a very limited interest to only specialists or something like that?
Yeah, not even to the rest of mathematics.
Not even to the rest of mathematics. Okay, great. So I think this is a great illustration of the brilliance of referees. Yes.
Thanks again.
More questions? I have one.
Yes.
So the first part of the talk, you get the impression that you have to sort of build a whole dictionary for each type of amplitude that you have. I mean, first 3 level, then you include the loops, and you get the impression that there is a whole new set of new actors in the translation that enter for each little complication that you add. So
that's really not so. I think that's I mean, after we understood things, for example, in the short amplitude, you can say the all loop object in one go. I mean, it's true. I think the real transition is, if you like, between trees and loops, and that's because of still a weakness of most of this approach. Although another thing that's happened in the pandemic is we're starting to deal with that. But I'll come to that in a second. A weakness of this whole approach is not only that it's perturbative. Yes, it's perturbative. But that at loop level, it talks about this object, which is the integrand, rather than the actual integrated amplitude. Now, at tree level, the kinematic variables are literally the ones that you see, right? The momenta of the particles. But at loop level, you have to have a new kind of thing, which is the loop variable, right? If you're going to talk about the integrand. So I think the real transition is not between trees, 1 loop, 2 loop, 3 loop, but between trees and loop, period. So you see that in n equals 4 super Yang-Mills. In n equals 4 super Yang-Mills, just the kinematic data for the external particles, which the amplitude only depends on these things, is given by a bunch of 4 vectors. They're called momentum twisters, but they're just basically the 4 momenta. Okay? They're simply algebraically related to the 4 momenta. So there's a bunch of 4 vectors. Your kinematic space is just n 4 vectors. I mean, again, very boring place. What the heck can you do in the sense of n 4 vectors? But that's all you have, n 4 vectors. Then each loop variable is interpreted as a line that lives in this, or plane that lives in this 4-dimensional space, a 2-dimensional plane that lives in this 4-dimensional space. Okay? The space of 2 planes in 4 dimensions is 4-dimensional, and those are the 4 loop variables. So that's it. That's your kinematic space, is n points and L planes. And in that space, you have to find a positive geometry and do all of that. And that's what we know how to do. So it does have one uniform definition and involves the same ideas, the same kind of positivity criteria, everything. If this talk was about the amplitude instead of these sort of simpler objects, then yeah, we could just begin with a half-page definition of the whole thing and then just see how all the stuff that we want comes out. But it does have this funny feature that it has these planes in it that are not really there in the actual problem. Now, for n equals 4 super Yang-Mills itself, over the past couple of years, there's starting to be some progress in some picture for what the non-perturbative geometries should be for the actual amplitude rather than the integrand. And it's related to very similar ideas, the Grassmannians, amplitude, positivity, cluster algebras. I mean, and in fact, that's one of the fascinating things, is that exactly the same kind of polytopes show up in that story as we're seeing for these surface things. And so they're even related in some funny way that we still don't deeply understand. Similarly here, in the story that I told you today, the real transition was sort of tree to loop, where you have to talk about these new kinds of variables that correspond to the loop guys. And then yeah, so so I think I hear what I sympathize with what you're saying. But I think when the objects are understood, they have a sort of more uniform definition. For example, the sort of conjecture that we have for what these surface hedra look like have nothing to do with, for any surface. Give me any surface, you draw the arcs, and then there's something to do with them to turn it into a polytope. And we're checking if it's true in general. I mean, it's working so far, but it's no distinction between tree, loop, this, that, the other. A larger complaint is why for n equals 4th degree unknowns we do one thing, and for phi cube theory we do another thing. And then for phi to the 4th theory, it's something else. And they're kind of, now phi to the 4th is related to phi cubed in some way, but that's their mea culpa. I mean, we don't, that's why we don't know the rules yet. But all I can tell you is that while they appear to be different, maybe even quite different on the surface, they're much less different than you would naively think. Or they seem to have connections between them, and so hopefully we'll understand it better. I think there was a question in the chat why the positive geometries are called positive, and I'm so sorry I should have said this during the talk. You'll notice that a very important feature of, the whole notion of a positive geometry is that you first have to talk about the interior of some region and then its boundaries. And positivity is crucially related to the notion of an interior. So you see this most easily. For example, let's say you want to talk about the points on the inside of a triangle. Let's say I give you the vertices of the triangle, you want to talk about all the points on the inside. How would you characterize the points on the inside? Well, one way to think about it is to imagine that the vertices have some masses associated with them, and look at the center of mass. The center of mass would be sort of inside the triangle somewhere. And if you varied the masses on the corners, you would move around everywhere that you want inside. But crucially, it's important that the masses are all positive. The masses are positive, and if you scan over all the possible masses, you scan over all the possible points inside the triangle. So the notion of positivity and of an interior are very intimately tied to each other. And so that's where the word positive comes from. If you just say you have 3 vertices, what region do you associate with them? Well, I could draw all the lines, but I've divided the plane up into 4 parts, right? In order to focus just on the triangle, I have to say also the word positivity. I have to say I'm interested in the points that are a positive linear combination of the equations.
Okay, are there more questions?
Yes, Nima, you mentioned a set of lines and a set of points. Were the points on the lines, as in this picture? If you can see it.
Sorry, in which context are you talking about?
In this conversation after your talk.
Oh yeah, no, I was thinking about the points in general position, in fact. So
right.
Yeah, so
and lines.
Yeah, I mean, at 0th order, everything would be in general position. But for example, if we're talking about, if you just give me, and in fact, positivity enters in 2 important ways. Let's say, even on the plane, let's say that you just give me n 2-dimensional vectors, and I'm blind, so I can't look at them. And I want to know what is the sort of convex hull of all of this region. Well, first of all, some of them might end up being on the inside. Even let's say they're given to me so that they're all secretly vertices of my polygon. Well, to know the order in which I'm supposed to draw the vertices involves some notion of positivity. So again, even if I didn't know, if I couldn't draw them, I could take all these determinants, if I thought about it projectively, and put a 1 on top of, make 3-dimensional vectors. If I take the determinant of any triple, if they're ordered properly, they all have to be positive. And that's what tells me that they're correctly ordered around the polygon. So even the sort of data for what specifies the convex region has some notion of positivity in it. And on top of that, in order to know that I should be inside the polygon rather than in another place from the extension of all the lines that divides a plane up into zillions of regions, it has another notion of positivity. So the sort of notion of interior of polygons involves two notions of positivity that are generalized in the story of the amplitahedron to Grassmann.
But back to your general position.
Yeah.
You have lines and points. The total collection is in general position, so the points are never on the lines?
Generically, they're not on the lines. I mean, of course, we can move them, and singularities sometimes happen when you move them to special positions.
Very good.
Yeah, and there's also a question about whether this kind of positivity is related to entropy. There's certainly, I mean, I think, well, I will say this, that the entire story of entropy bounds in quantum mechanics. I mean, really, the reason quantum mechanics is not just dumbly linear algebra. Why is quantum information interesting at all, right? Why is the subject, why does it have any beef? If you're very naive and you're an undergrad, you think quantum mechanics, if you're a precocious smart aleck undergrad, you say quantum mechanics is linear algebra. What's the big deal? Well, what makes it a big deal is that it's linear algebra, but where matrices with positive eigenvalues are important. Okay, so you don't just care about random operators; you care about things like density matrices that have positive eigenvalues. And it's that positivity that's the source of all the interesting non-triviality in quantum mechanics. So, for example, Bell's theorem is just a very, very lame way of talking about a nice convex geometric fact about density matrices. If you take 4x4 density matrices, there's which you get for a 2-qubit system. There's a nice question you can ask: which one of those 4x4 density matrices can be written as a positive linear combination of the tensor products of 2x2 density matrices in two previously selected subsystems? And the answer is not all of them. There are some convex region that is cut out by them, and the whole region is bigger than that. So the fact that the convex region that's cut out by them are the ones that satisfy Bell's inequalities, and the rest of them is all of them, which is more. Okay, so these sort of 50 years of philosophical blah 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 about Bell is just one totally trivial fact about this this interesting statement that the space of 4x4 density matrices is larger than this sort of simple convex set that you would get. But again, what drives it is a positivity. You want to ensure that you can write it as a sum of the product of density matrices in the 2-qubit subspaces with positive coefficients. Okay? So, the kind of deepest sort of theorem about entropy, of which so many other things somehow follow, is the subadditivity of entropy. This goes back to Elliott-Lieb and collaborators that gave sort of complicated proofs relatively complicated proofs in the 1970s. And to my mind, there still isn't a super duper simple conceptual proof of this extremely simple to state fact. The nicest proof is associated with David Petz from the mid-2000s, I think. But still, I think for such a simple and deep fact, it still doesn't have a proof. To me, a beautifully conceptual proof yet. Petz's proof is very nice, though. Anyway, this again crucially relies on positivity. So there are some, but it's a positivity of Hermitian matrices. So there's some hermiticity structure in the quantum mechanics, and positivity and hermiticity has some positive of probabilities, and hermiticity is associated with some quite non-trivial positivity properties, which are the kind of engine of the entropy rules in quantum mechanics. Again, the strong subadditivity being the most non-trivial of all of them. The rest of them are kind of fairly trivial. The strong subadditivity is something really beefy and very non-trivial and interesting. Anyway, I've had this sort of fantasy for a while that positivity in quantum mechanics and the positivity that we see, especially in the context, not of the things that I've talked about here, but in the context of the positive Grassmannian and the amplitahedron, might be related to each other. But there's a sort of basic difference that in our story, there is no Hermitian structure. It's even simpler. You can explain it to a kid in high school. And the positivity just involves determinants. Okay, so just various determinants have to be positive. Now, there is actually a close connection between positivity of eigenvalues and positivity of determinants. Something else you learn in high school, if someone hands you a symmetric matrix, even a Hermitian matrix, and you want to check if all the eigenvalues are positive, how do you check it? You don't want to sit there and diagonalize it and give it to Mathematica, but there's a one-line way of checking it. You just take it and you compute all the minors of the upper adjusted square matrices. This criteria goes back to Cayley in the 1800s. And the matrix is positive if and only if all those determinants of those minors are positive. All the minors on the 1 by 1, 2 by 2, 3 by 3, 4 by 4, all of those are positive. So there's even a connection between the positivity of quantum mechanics and the positivity we talk about all the time in the Strassmannian business of positive minors. But they're not exactly the same thing. And I think it would be fascinating if there was some way of connecting them. All I can tell you is that there is some kind of non-trivial positivity in quantum mechanics, which is associated with the positivity of probabilities, and it would be very cool to establish a closer connection between that and the positivities we can see. Yeah, sorry, that was a long answer to your question, but it's something I've thought about a lot, so that's why.
So if there are no more questions, I would like to thank Nima again for his efforts. And I guess that it falls to me to close the workshop, but being the Christmas workshop, you will allow me to do it with wine, okay? So being the Zoom master is like being a priest, you get to drink in the name of others. So here is to all the speakers for their efforts, the organizers, and especially the participants for showing up. And let's hope that we have a better year ahead, and that in 1 year we will be able to meet more physically in the Christmas workshop. So salud, especially to everybody.
Yours.
Thank you.
And thank you again for coming. So enjoy. Bye-bye.
Thank you. Bye-bye now.
Bye-bye, Nima.
Great seeing all of you. Hey, Paolo,
Bye.
great seeing you. I didn't see you there. Great.
Yeah, I was here all the time.
All right, good.
All the time.
We'll talk
All the
later.
time there, yeah.
Yeah.
Bye-bye, everyone.
Bye-bye.
Bye-bye.